So what we're looking at today is force time graphs. It's just an impulse. Remember yesterday we learned impulse was this idea of a force multiplied by some amount of time. That is an impulse. If you push on an object for some amount of time, it's going to speed up or slow down. You're going to change its momentum. Well, when we did that yesterday, we were looking at average forces on an object. We were saying, hey, look, that car was slowing down with a force of 1733 newtons in the negative direction. Or the baseball bat was hitting the baseball with some force. But if we actually think about an object striking another one, whether that be Rocky Balboa throwing a punch, or your car running into a street pole, you doing some hardcore parkour, or a golf ball turning into like a pancake whenever it's hit by a golf club. Those forces acting on the object change over time. If you think about a punch, as you're getting hit, their fist is in contact just barely at the beginning with your face. So there's very little force there. And then they drive their fist in, then your face deforms, and there's more force, but then your face starts moving away, and their punch starts gliding off, and there's less force and less force. That force amount is changing with time. And since this force amount is changing with time, we have to go and actually think about how to figure out what the total impulse is being applied. And this happens with golf balls as you hit them, as you're like rolling on the ground, whatever the thing is. When objects are interacting, when they're colliding, when they're impacting, that force is changing. And because of this, we need to figure out what's going on here, okay? So these are in our notes, which are sitting in our Google Drive, and you might just have them from yesterday. They're on the backside. What we did yesterday was with a constant force or an average force, we just multiplied forces and times. That's what we're doing. When we think about that impulse equation, we just say J impulse is F multiplied by T. And if we actually think about what multiplication means, like all the way back from third grade when we were doing that and kind of learning it, one of the things that we saw with multiplication is you're really kind of setting up a grid or a table. And if we think about this, if we were pushing on an object with a force of 3 newtons, and we pushed on that object for a time of 4 seconds, you could say, hey, the 3 times 4 is 12. So let's say Jack has a job and you're making $10 an hour, okay? If I want to figure out how much money he makes in 20 hours, we would just do 10 by 20, right? We just add up the hours. So if I know how much impulse is in one block, all I need to do to find the total impulse is figure out how many blocks are underneath this curve. And to do that, well, we'll go all the way back to our elementary days and we will just count the blocks. That's it. We don't have to do anything fancy here. We'll just count the blocks. You do have to make a little bit, so we'll just count these blocks up, and we will have to do a little bit of an estimation here, because some of our blocks are like kind of cut in half, so just use your best judgment, okay? So let's just do this. Let's just count the blocks together. Let's just do our whole blocks first. So 1, 2, 3, 4, 5, and then everything else seems to be cut a little bit, but this block right here, I'm just going to call that 6. Like, that edge is so slight, who cares? Let's just call it 6. Down here, this block is like barely cut off. We're just calling that 7. Let's just call this one 8. Like, it's close enough. Let's see. Maybe between this block and this block, maybe we'll just call that 9 together. Because it's like one was there and one's a little smaller, so together they're a 9. I don't know, but that's pretty close. And then maybe this block and this upper piece we can call like 10, so that goes away. And then maybe this is like an 11 between here and here, so we're kind of at like 11. And then maybe that upper one's 12. Maybe it's a little less, maybe it's a little more. I don't know. It's an estimation. if you got something between like 11 and 13, we could feel comfortable with that. But you cannot say that it's 16, because 16 would be this entire setup. And we know that we're not using these two regions here. So you can't tell me 16, you can't tell me 15, you can't tell me 14. You also can't tell me it's 5, because we hit 6 just really quick on the inside here. So something between like 11-ish and 13, that's a good estimation, give or take a little bit. And that's what we're going to go with here. So we counted 12 in our example. If you counted something a little different, that's totally fine. So if we just want the total impulse now, well, this is just train tracks or fence posts. We know we have 12 blocks, or 11 or 13 or something in the middle. And we know that our impulse is 0.5 Newton seconds of impulse per block, right? We quickly notice that our blocks go away, and now we just have a total impulse applied to the ball. So our total impulse applied to this croquet ball is 12 times 0.5, or half of 12, which is just 6 Newton seconds. So that's not too crazy, right? We feel pretty good about that. That's the big takeaway from what we've done here on reading these graphs. All we've done is said, look, there's a graph, it has a curve on it, I need to find the area. If you can find that area by counting blocks and figuring out how much each block is worth, you did it. You found the total impulse. So it's nothing crazy there. In part C, though, we are asked to calculate the speed of the ball as it leaves the mallet. Well, we can use what we already know about momentum and what we just found with the total impulse to close this problem out. Previously, when we did problems like this, we said Ft equals m times Vf minus Vi. But recall, this Ft is the impulse. That is how F, a force multiplied by t, a time, is defined. So if that is the impulse there, then instead of writing Ft, we can just write J. We know what the total impulse is from the graph. So we can just drop our 6 Newton seconds into this equation that we've already used and just set this up nice and straightforward. JT is 6 Newton seconds. This will be equal to the mass of the croquet ball, which was 0.4 kilograms. And then it's a final velocity minus an initial. We're looking for the final velocity here. We don't know what it is. And if this croquet ball started at rest, you know the initial velocity must then be 0. So I'm not even going to put minus 0 because nothing's going to happen, right? So the big important feature is that this Ft we had before is just the total impulse. We just drop in the area of the graph, which was very straightforward for us to find. We don't do anything to it. And then if we just want to find the Vf here to actually finish this problem out, we'll just divide each side by 0.4. Divide by 0.4. 6 divided by 0.4 is a number. Let's just roll our calculators here. We get a value of 15 meters per second. And that's it. That's finished. Nothing more to it. We know impulse equals a change in momentum, and now, even if we have a variable force as given by some weird graph, we can still estimate a good value of that impulse and use it for our equations. So this type of problem is finished. In future things that we'll be doing, we'll be looking at a few of these examples a little bit later on. And we'll also be starting to look at what happens if momentum is acting in 2 dimensions. But for now, we are finished. Adios, and take it easy.